afternoon and welcome everyone to this XP Live webinar. My name is Catherine Tran and I'm part of the marketing department here in the XP Solutions Portland office. So today's webinar, we will demonstrate the steps involved in building a 1D, 2D model from scratch. So if that's a topic you're here for, then you're in the right place. And one more note here for those of you who may not be familiar with XP Solutions, we have a long history of providing high-performing software solutions. Our intention is to make sure that in your work you can model with confidence. So this means that we strive to provide excellent customer service and support, and that we offer continuing education opportunities like these for engineers in our industry. Today's presenter is Anthony Kuch, our Vice President of Client Services and Product Owner for XPSWM and XPStorm. Tony has been with XP Solutions for over 24 years. He's trained thousands of XP users, provided technical and engineering support, and continues to drive the development of XPSWM and XPStorm. Tony is our XPSWM guru, which means that today you are in very good hands. Thanks for joining us today, and here's Tony.
Thanks for that introduction, Catherine, and good morning or good afternoon, depending on where you're joining us from. I'm really excited to have this opportunity to present today, especially talk about something that I personally find exciting and should be beneficial for you. The agenda today is that I'm going to spend just a short few minutes talking about perhaps the typical data in a 1D, 2D model, maybe what do I mean by a 1D, 2D model. And then I'm going to spend the bulk of the webinar building a 1D, 2D model and highlighting the workflow that I'm choosing and why I'm doing what I'm doing, how I did it. This webinar is going to be a little bit different than most of our webinars in that this one is a little bit more instructional on how to do the work inside of the XPSWM interface. So in a way, it's a little bit of a training session more than our typical webinar, which is talking about the theory, and we go very quickly over how you do it in the software, but this is a different perspective. For 1D, 2D modeling, basically we're talking about integrated 1D, 2D modeling. We have a nickname called XP2D, which basically means XPSWM or XPStorm with the 2D portion activated or turned on. We try to take advantage of all the good things in 1D and all the good things in 2D, minimize the disadvantages by solving a model that is integrated in the sense that we're solving it at the same time. The typical kind of data involved in a integrated 1D, 2D model is essentially a 1D model. Can't underemphasize this. You should have an existing working 1D model before you try to integrate it into 2D. And then on the 2D side, there's really a simple set of required data. You need dense surface data. For example, perhaps something like every 3 feet or every 10 feet you've got elevation data. And this automatically sources the 2D model with the elevations for the grid or the mesh. And then we need roughness values. All cells need to have essentially elevation and a roughness. And we provide this roughness through 2D land use, which are polygons. You could draw them or import them. And then, obviously, 1D, 2D model, we need the connections to 1D. And this is where I'm going to spend a little bit of my time building it, although our previous webinar, we did talk about the connections between 1D and 2D. The topography is derived automatically. We have a digital terrain model, an XP10 primarily, although you can reference grids. In the 2D job control settings surface section, you can actually reference a grid, which means that you could do a much larger grid than you would be able to triangulate and present in the XP interface. So there's basically surface data, and we overlay a grid, and we automatically extract the cell center elevation, the ZC point, the cell side elevation, ZU, ZV, and an elevation at the grid corner. That elevation at the grid corner doesn't have a hydraulic purpose. It's really only for presentation. But the ZC, ZV, ZU points are used in the hydraulic computations. The cell center tells us how much water is in the cell. The cell side, this is where we center the momentum equation, and we will be deciding if water can flow from one cell to the next. It has to be greater than the cell side elevation. The 2D domain, which is basically our grid, can have within it both active and inactive area polygons. This will turn cells on or off. An example of an inactive area would be perhaps buildings or areas where you're computing 1D, like a 1D pond or a 1D channel. You wouldn't want to double account for the storage and the conveyance, so you remove these cells from the 2D computation with an inactive area polygon. We're going to use both active and inactive area polygons in my model build. All hydraulic models need boundary conditions. In a 1D hydraulic model, a boundary might be the inflow or the outfall. In a 2D model, those boundaries, one more dimension, end up being a line rather than a point. So along the edge, for example, or within active area, you could create head and flow boundaries. And we're going to create a head boundary to allow the water to go off of the 1D, off of the 2D active area and disappear from the model. So at the edge of our computations, we're going to have a head boundary to allow flow to run off. Otherwise, it would pile up at the edge and just build up on the 2D surface. So it acts basically like an outfall would for 1D. As I mentioned, in the simplest case, a 2D model is elevations and roughness, and we get the roughness to the model with what's called a land use polygon. So we're going to import from GIS some land use polygons, which is going to give us the roughness and optional infiltration for each of the cells. To introduce flow to a 2D model, one of the options is a polygon. The polygon could be for flow and for rainfall, like to do direct rainfall on grid. That's a possibility. Inevitably, the terrain data is perhaps missing something because it's dated, or it might be missing something because of detail, like maybe you're using a grid, like a DEM, and maybe it's every 30 feet or every 10 feet. And this thing that you want in your 2D model is smaller than that, and it's missed in that sampling of points. Well, you can supplement your grid for the purpose of the 2D model with ridges and gullies. These are break lines or lines, right, that you're giving elevation, and they will be making changes to the 2D model where the surface data is insufficient. There's polygons, they're called fill areas. I put here cut or fill because the polygon of a fill area just has a new elevation, so it ignores the grid and you supply a new elevation. You might do this because of a pond. Perhaps you have a proposal to create a pond, but your surface doesn't have it dug in, but you do that after the fact. The layered approach of XP2D allows there to be like a static surface, and then you can add other things to supplement it. And if it's more complex than a constant elevation, we have elevation shapes, both static and dynamic. Dynamic means it changes over time. Dynamic elevation shapes could be used for things like levee failure, dam collapse, a fence that falls down because of high water on one side, things like that. And then, of course, we're making an integrated 1D, 2D model. The connections to 1D happen within that 2D domain, creating what I've coined XP2D. The typical kind of linkage, we're going to concentrate on this more complex one at the bottom, listed as 1C. In here, we're going to be modeling in 1D from the channel banks because that's where it's most descriptive. Like the 1D model does a much better job describing the shape than a 2D model would with coarse cells. And then in the floodplain, we're going to be modeling it in 2D. And in plan view, how that looks is you can see a grid here overlaid, And then there are cells missing where the river is placed. So we've made those cells inactive because we're already doing a computation in 1D. So you don't want to double account for your conveyance. Then you'll notice off to the side here, there seems to be like a storm sewer network. And in this case, the manholes are attached to the cells. And the following thing could happen. You could have a river that floods its banks, flows over land, finds a storm sewer, gets captured into the node, flows down the pipes, pops out somewhere else, goes overland back into the river downstream. Of course, this is somewhat complex hydraulics, and we simulate this in XP2D by solving the 2D and the 1D simultaneously and exchanging the water between them. There's always a mass balance between the two. So when that linkage happens, let's say for a manhole, let's say you've got a storm or combined sewer, and you've got essentially a case where water could surcharge in the manhole. It could reach the surface. It could then flow over land following the terrain. It could find manholes to be captured into. But you're also allowed, as you've observed in the real world, that an inlet might have some bypass. Perhaps you're capturing some and bypassing others. This would be a case of inlet capacity at the node, but there's also a 2D approach to restricting that capture, and that's called 2D inflow capture. 2D inflow capture can be enabled at any node where you can put in a specific equation for it based on the size of the inlet or the curb opening. And globally, you can set 2D inflow capture with the same kind of equation approach where the captured flow equals a coefficient times a depth raised to an exponent. Now this is a classic hydraulic equation. With an exponent of 0.5, this represents an orifice. If the exponent is 1.5, which clearly you can enter because it's a user field, at 1.5 it's more like a weir. And then the coefficient, the size of this coefficient is really related to the size of the opening. So you're putting in here, for example, if you wanted to model orifice, orifice area, orifice coefficient, etc. So this is a generic equation, but it fits weir and orifice very easily. The hardest thing to set up, the thing that will take the most time, is where we're going to connect the channel between 1D and 2D. It takes three types of elements. I need an inactive area polygon so that I don't double account for the conveyance and storage in the channel. I'm already modeling it in 1D, and so I take it out of 2D by nullifying the cells. These purple and yellow cells are essentially been disabled for 2D calculations because of the polygon that I've drawn in the shaded blue. Now on either side of this, there's a darker blue line here. This is called the 1D 2D interface line, and it's the boundary for the 2D model. It's where the flows go from 1D to 2D and from 2D to 1D. They're introduced along this line. The magenta colored cells are the ones that are captured for the purpose of this 1D 2D interface line. And the 1D 2D interface line is connected to the nodes through what we call the 1D 2D connection line. The 1D 2D connection is, if you will, it's something that's transferring the water level between 1D and 2D. And it acts virtually as a conduit that's exchanging the flow between 1D and 2D. So how it works, let's say there's a water elevation at this node 158 and a water elevation at node 159. In the 1D model, you would linearly interpolate the water elevation down the link. Likewise, because it's connected to this point and this point with the connection lines along the 1D 2D interface line, along the 1D 2D interface line, we linearly interpolate the water level in the channel. And then, based on the elevation of the cells and the elevation of the water in the floodplain, we can spill the banks of the river link all along these locations. So in 2D, it specifically spills at the cells, And in 1D, we are moving water in and out of 1D at the nodes. Let me tell you a little bit about the data summary that I have. So I'm going to start with an aerial image with a world file. This is going to stretch and move the aerial photo to the right location. You know, it's got a coordinate system. Then if I draw something 100 feet, it's in the view, it's 100 feet in XP, etc. I've got also some topography in the same coordinate system. A 2D model, as I mentioned, is elevations and roughnesses. And so I'm going to start with some topography that's in the same coordinate system as my aerial photo. And I have a working or existing 1D model, and I will kind of demonstrate to you that it's a 1D model that's already solving, and there's perhaps a reason to make it a 1D 2D model, which I'll show based on some of the hydraulic results. It doesn't have any dual drainage, so in the location of the roads, for example, I just have single conduits for the to represent the closed subsurface pipes, and if they surcharge, well, then they can follow the terrain in a 1D 2D model. If you did a 1D model only, you would probably make it a multi-link with a natural channel. But that's very subjective to the quality of the modeler, whereas we've got terrain data, and if it should follow the terrain, then in a 1D 2D model we can take advantage of that. And then finally we need land use polygons to introduce roughness primarily, and optionally we could have things like infiltration occurring. And so these happen to be in GIS files, which I can easily import. So that's essentially the four main components that I'm going to be working with. You could say with three of them already in existence in what's going to be my starter model: the aerial photo, the working 1D model, and the topography. It's really already there. I'm just going to be adding 2D land use polygons. So let's get to the modeling. So a lot of my webinars are actually going to be live within the software. The steps I'm going to follow is essentially I'm going to start with this 1D model. Is it running? Is there a need for making it a 1D 2D model? And then the steps, I'm going to add a 2D grid and land uses. I'm going to make parts of it active based on where do I want to do the 2D computations. I'll add a head boundary on the edge of that to allow water to escape. You know, it's kind of like my outfall. And then I'm going to connect my 1D to the 2D model, basically connecting the manholes and also the channels. The most of the time will be spent connecting the channels, in fact. I'm going to then add some plot output lines and points. These are recording stations. Any flow that crosses the line becomes a hydrograph, and the elevation over time and the velocity over time can be seen at a point. So you add these before you solve. We'll set up the 2D job control. We'll troubleshoot any issues, or I'll teach you how to troubleshoot. And then at the end, maybe once we've got some results, I can even spend a little time on the exporting of these maps, you know, the inundation map. All right, so let's switch over to the software now. Here we are. I've got the software at the state of the opening banner, and I'm going to start with my starter model. Here's my starter model. Let me just perhaps turn off the background image for a moment so that you'll be able to better see the links and nodes. Down here at the most upstream part of the model, I've got natural channel, and in the interior of the model I have some closed conduits. The nodes which have a prefix of MH, these are basically my manholes, and they are set up to receive the flows that are computed in the runoff mode. So if I switch to the runoff mode, you'll see there's various nodes that are active, so they're going to be changing the rainfall to runoff. Also, at the most upstream part of the river, I am passing a hydrograph that represents perhaps an off-site flow that travels through the system. and I'm kind of measuring the impacts of the development in this area. And as I mentioned as well, although I won't leave it on very long, I've got a surface model here as well. Perhaps in this case, for the 1D model, it may have been used to cut the cross sections or set the ground elevations for each of the nodes. But it's not a required part for 1D modeling, but definitely required for 2D modeling. So let's do a save as, because this was a starter model, and so perhaps I'll just remove the word starter. All right, so here we are with our model, and let's solve it. As I told you, it's good advice to have a working 1D model when you want to make a integrated 1D, 2D model. You know, it's a big task, and I would start there, and once you have a working 1D model, you're kind of ready to go. So if I switch to the runoff mode, I'll just kind of let you see there's some model results here where I'm producing flow from rain, basically using a hydrology method. And so these are the flows that are sent to each of the inlets. And then in the hydraulics mode, if I select, for example, MH04, hold the shift key and click here into the river, so I'll just look at this small stretch. I could look at what we call the dynamic section views. It shows me the profile, the cross-section, and the hydrograph all synchronized together. If I play, let me rewind this to the peak, and you can see that, in fact, a couple of the upstream manholes flood. They show this water symbol that the hydraulic grade line has reached the ground surface. So I might want to, rather than just lose the water at those manholes, know where the flow goes based on the terrain, and that's part of the motivation for an integrated 1D, 2D model. If I look down here, let's say starting at node 100, I'll hold the shift button and click down here where it goes from open channel into a closed system. Again, I'm going to choose the dynamic section views. I can play this. Let me just remove the XP table here so that there's a little bit less real estate used up. And as I play it, I can see the water is backing up before the culvert. In fact, a little bit further down, water is surcharging out of a manhole. This water is just lost here. This water is just being built up before the culvert, not lost. I know that because the hydraulic grade line is above the ground. And I really want to know from this 1D model, where is this water going? How is it completely interacting within the urban development? So from this point, I know that I have a good working 1D model, and I want to create a 2D model. Our first step would be to add the 2D grid for the area of interest. I'm going to put the background image on so that when I create the grid extents, and you'll notice that under 2D model I do have this layer available already called grid extents. That's the only one we automatically generate, but if by chance it wasn't there, you could right-click, add new layer, and add a grid extents layer. But it's already here for me. So I'm going to choose the polygon tool because this layer, this grid extents layer, accepts a polygon. And in order to draw a polygon, we click to create the vertices, and I'm just going to basically go to each corner. And on the last one, I'm going to double-click. Double-clicking ends the polygon drawing and creates the grid. With the pointer tool on the toolbar, I can then select the polygon for the grid extents. I could right-click on it and choose Properties. I could double-click on it, or I could right-click and choose Properties in the Layer Control panel to get to the Properties dialog for the grid. Now that I'm in this dialog, I'm in here primarily to set the grid size, and in this case I'm going to use about 3 meters, or about 10 feet. This is a fairly typical size for an urban area. I guess you could probably go down to as low as 3 feet or 1 meter in some cases. But because there's houses and the flow is going in between houses, around houses, maybe I want to see the high crown of the road dry where the gutter might have flow in it. In order to get that kind of detail, you need a fairly small grid step size. There's also the ability to change the orientation angle. If I put it at 0, I can just type it in, but there's a handle in the plan view that also allows you to change the angle. I'm just going to make it go straight north. If you were motivated to make it have a change, feel free to put in an angle in here. And click the OK button. If I return to this and choose Properties, you can see the cell count. And it's also possible to tick a box that says that you can show the cell center elevation. So if I was to zoom into the model now, and I zoomed in enough, and there was enough space to show the text for the cell center elevation, it would definitely appear. So as you can see here, I've got different elevations for every cell. Let me save. The next step is to add the land use. Now the land uses are added to a model through the global database. There's a section called 2D land use. You can just type in here, add a record, you can add one. For example, when you add it, you could then look at the data. I'll edit this. For example, I'm setting a roughness here for the roads to 0.025 Manning's Inn. You could also turn on optional infiltration. I'm not doing it in this case, but it is possible to set detail for infiltration losses into every cell. Maybe even more applicable when you do a rain on grid. Well, once you've built the items in the global database, they then appear in your layer control panel. As I mentioned, one of the things that I have already for this model is land use polygons in GIS, and it's a simple right-click to import them from GIS. So I'm going to import my roads post-development. The pasture is going to be my default land use, so I have no polygon for this one. But for the buildings, I do have a shapefile to bring in for the buildings. And you see 411 buildings were brought in with about 3,000 vertices. For the ponds, I'm going to import from GIS. I have a ponds post-development shapefile to import for that. And finally, for the vegetated creek, I will import some polygons for them, which will be my creek post-development. Now, I'm going to turn off perhaps the grid layer, and maybe even for now the background image, so you can better see all of these land use polygons that I've brought in. So that's the main part of a 2D model, right? Elevations and land uses for the roughness. So now let's get down to a little bit of the detail. I'm going to show the background image again, and I'm going to decide based on this picture where I want to have active in the 2D model. And I'm going to add a new layer called the active areas. And I'm going to digitize a polygon in that layer with the polygon tool. And I'm just going to go around the model here, across the top, maybe from here to here, going around. Perhaps I should use the terrain to give me some guidance on where this should be, but that should be fine, and I'll double click. So this active area, I'm going to essentially say that there's a default for the 2D grid, which will say that it's inactive, and then the active part will turn on those cells. So within this sort of egg shape that I made, I'll be able to do the 2D computations. I'm going to add another layer, and this layer I'm going to add is going to be called the head boundaries. So it's lower elevation up at the top near that node 94. And I'm going to create a head boundary, which is a polyline, which if the snap tool is turned on, then I can simply just click and it will change to a crosshair when it's snapped to a vertex. And you can follow along pretty easily, like all the vertices, with a command where you hold the shift key or the control key. One goes one way, One goes another way around the polygon. That's what I want. I'm going to double click and that creates the head boundary. Now the head boundary, I can select it, right click and edit the data, and in this case I'm going to say that it goes from 0 to, let's say, hour 6, and the elevation is 35, 35. Why did I pick 35? Well, 35 just so happens, using the section profile tool here, to be lower than any elevation that I can find in the terrain. So this will essentially act like a free outfall. It won't introduce water because it's not higher than the land. So the head boundary at elevation 35 as a constant is always below, so any 2D water can run off the top. So, you know, I could extend the model further perhaps, but how far would I have to go, right? All the way to the ocean? You know, who knows how far you would have to study, but I'm saying I'm only studying this area. This is the edge of my study, and so I use as a boundary a constant elevation over time. Let me clean up the picture so it makes things very visual for you. I won't have on the background or the 2D or the active area or any of these land uses for now. I'll just turn them all off, perhaps the head boundary too, and go to the next step. I'm going to save this. I'm going to now connect the manholes and the channels. It's pretty easy in the case of a manhole. It's simply a radio button that says link spill crest to 2D. So when the water reaches the spill crest elevation, it then spills into the connected cell. This is something that I could copy, so using the 2-page copy icon in the upper right-hand corner of the dialog, I can click on link spill crest to 2D. It's basically copied to the clipboard. I could then select the nodes that I wanted to make this change to, so perhaps it's the ones right here in the middle of the model. Not these ones that are in the river, so maybe perhaps I can turn those off with the control key and click with the mouse. And then to paste this, you could use the paste icon, or edit menu has paste. You could right click on here, there's paste, and of course control V, V as in Victor, it has paste as well. So now each of these manhole nodes then, if I just go to an independent one, you can see as link spill crest to 2D. That's all the work there is to connect a manhole to the 2D surface. Pretty easy. The thing that takes a little bit of time is connecting the channel because it requires the 3 elements that I mentioned, or the 3 2D objects. I need a layer of inactive areas so I don't double account for the conveyance. I also need a layer called the 1D 2D interfaces to introduce the water to the 2D model from 1D, and this has to be connected to the nodes through a 1D 2D connections layer. Now I've made the 3 layers, and it helps in order to be able to see the surface model. So let me zoom in down here and I'll start connecting this channel, if you will, to the 2D by using those 3 elements. I'm going to start first with the inactive area. It accepts a polygon, and the polygon should be equal width down the link. How wide is it? Well, I can see the cross-section in orange here, so I know how wide the 1D cross-section was. And so I'm going to start there, and I'm just going to digitize along the top of bank around that width all the way down the links that represent the channel. Here I am kind of following the contour that represents the top of bank all the way to this road. And over here to this side, and similarly follow the channel width as defined by the cross-section there that I just snapped to. I'm just clicking. Every time I click with the mouse, it makes a vertex. So again, this is the part that's already modeled in 1D, and so I'm taking it out of 2D by saying it's inactive and then double click to end it. Looks like I got a little wider here at the very beginning. That's fine. You can always select this and then grab the vertex and move it to a better spot. Let me save. That's good progress. So again, this is for the purpose of not double accounting for the conveyance. Next element I need is the 1D 2D interface. It accepts a polyline, and this polyline can go from snap vertices on the polygon, but remember the follow along command. You can just hold the shift key and then go to this vertex and double click, and it creates the 1D 2D interface all along that polygon in like an instant. You don't have to go and find each vertex. Again, this is used to introduce the water to the 2D model, and ideally it's along the top of bank. That's where the channel spills. And so you make your inactive area and 1D 2D interfaces follow along the top of bank. You might say, well, why didn't I close it? Well, this is the beginning of the model over here. So, you know, is the water really going to spill upstream into the, not really. So it spills its banks, and it could spill over the road. So that's why I have it on 3 sides. It's not necessarily wrong to make it on 4 sides. Finally, I need the 1D 2D connections, and it's a little bit easier to see these if perhaps I turn off the inactive area and the surface. This is a layer that accepts the polyline, and I'm going to draw it from the node to the interface line, or from the interface to the node. It doesn't have any direction. And I'm picking these points that are close by, because this is where we're saying the 1D model elevation equals the 2D model elevation here. And we need this, of course, also for the upstream part. So I could do the same up there. However, I will just, maybe for the sake of time in the tutorial, go to a finished model that has that done. So let me just go more completely down here and describe other things that we might want to do. Since there's an inactive area polygon here, then there's not going to be any, in plan view, 2D flood result. But it might look odd to see no water in the channel in plan view. There's a way around this, and it's called water level lines. Water level lines can be added to a link by selecting them, right-clicking, and then choose water level lines, generate water level lines, and I'm going to generate it for the selected links with a minimum distance of 20 for each of them, and I'll go 30 to the left, 30 to the right, and click OK. This then will display the water level lines for me. Right now they are going beyond the inactive area, or beyond the limits of the 1D 2D interfaces, and ideally they should be trimmed. So I'm going to right click and choose water level lines. In this case, trim the water level lines to a polyline or polygon. Click this polyline and it will automatically trim them. You may need to perhaps manually adjust them by clicking on the head or tail. They shouldn't cross each other, but you can just go in and grab the head or tail of a certain polyline for these water level lines, and you can just edit them. That will make a nice picture of showing the flood result in the inactive area, as well as, you know, as it is in the active 2D area part. So of course this procedure that I've just done needs to be done as well for the northern part, but I already have that done. If you double click on this node, we typically pick link invert to 2D for the river, but whether it's link spillcrest or link invert, it really doesn't matter. It just needs to be linked to 2D. It spills along the elevations of the 1D 2D interface line. Next step in my steps that I had outlined in my PowerPoint was to go and create what we call time series outputs. Whether they be flow lines or head velocity points, these are things that are going to record during the simulation. I'm going to put the aerial photo back on, and then I'm going to right-click on the flow line and define the flow line I'm going to create one between these two houses. I know that it's low elevation in here, and from experience I've seen flow go between the houses. So drawing this line means it's a recording station, and during the simulation it's going to record a hydrograph for all the flow that crosses the line. I showed you earlier in the 1D model that in the upper left-hand corner that this manhole number 4 flooded. So if I define a flow line up here, maybe across the road, maybe I'll call this overflow. Any flow that goes down the road would cross this line, and I could then have it presented as a hydrograph of flow that went down the road because of the surcharging manhole. I also know from experience, as an example, that in this intersection here there is a lot of water elevation and high velocities. So for that I'm just going to right click on head velocity and choose define a head velocity point. Stick it right here in this intersection. I'll call it intersection. And it's again going to be recorded here what the water elevation over time is and what my velocity is at that spot. So this is kind of all the physical data to create a linked channel and storm sewer system. Now in order to solve the 2D model we need to set up some 2D model settings. We turn the 2D model on with this tick box. We can set a time step. The rule of thumb for the time step is the cell size divided by 6 for US should be stable, or by 2 for metric models. So a 1 second time step should be just fine for a 3-meter cell. We can set here which land use from my global database represents my default land use when there is no polygon specifying something different, and I'll choose pasture. If I remember right, it's 0.06 as a Manning's N. We can also make the cells of the grid by default inactive, which is fine because I drew a polygon of active to turn on the area where I wanted to do the computations. This next item is the criteria that's used to decide whether a cell is wet or dry. A value of 0.002 means 2 millimeters. So if there's less than that, the cell is dry. If there's more, the cell is wet. A wet cell can compute and decide, where the flow will go if it's going to flow to its neighboring cells. I'm going to go to the model output now, and I'm going to specify that my model output is every 60 seconds for the maps. So every minute I'm going to have a new map of, where's the water, depth of water, etc. For the map result types, I'm going to go more than just the default of velocity, depth, and elevation. I'm going to add hazard. Hazard is the product of velocity times depth. In places where 2D modeling is very advanced, they make hazard maps because shallow, fast-moving water is also dangerous to life and property. People can be swept off their feet, buildings can be moved off their foundation because of fast-moving water, even though it may be shallow. There's a levels section in the 2D job control, which is important in order to fix the busts in elevation that may happen between 1D and 2D. In the first one, the cells along the 1D 2D interface, if they are lower than the channel bed, which doesn't make sense since I told you it should be along the top of bank. That's where a river spills. It doesn't spill below its bed level, but if you were picking really bad locations, then this will automatically fix and at least raise the cells to the bed level. The next one is a condition for the manholes where the top of the node may be below the 2D grid. How could you connect in that case? And so adjust lower will automatically lower the cell that the manhole is attached to, lower that elevation down to the top of the manhole if it happens to be lower. I'll take everything else, the rest of the defaults, click the OK button, and basically I'm ready to solve the model with the exception that I didn't connect 1D, 2D for the channel downstream. But I have that done in a finished model. I gave you the process for the upstream part. So let me close this. Perhaps I can save my changes and let me go to the completed model, which already runs. By the way, this takes around 4 or 5 minutes to solve, and hence by loading the solved model, then we get to not have to wait the 4 or 5 minutes. So once the model has been solved, again, the solving is just clicking on this icon over here or pressing F5, or Analyze is the solve menu. Once it's done, it would come back and it would look like this, and you may see some text on the screen. This is the diagnostics layer. If you right-click, it has a property in the data section where you could turn on all of your messages. I happen to have 48 of them. It's a mixture of warnings or check, unstable, or other messages, etc. I don't have any errors because this successfully solved, but if it didn't successfully solve, if you had a problem in your 2D model, you could troubleshoot it by looking at the diagnostics. The errors would actually be in red. You can see I got a yellow warning here, and I've got many, many check messages. Let me turn off the background image so you can actually read some of these, and perhaps I'll zoom in. So you notice this check 22118, it says that it lowered the cell center by 0.06 meters to the 1D node. This is basically because there was a cell elevation that was higher than the spill crest. So how could it possibly connect? And so in the 2D job control, in the level section, I told the program to automatically adjust this. Well, it did, but it told me whenever it had to make this adjustment. At nodes, perhaps where the manhole was above, there's no message. All right, no message there, because it didn't have to make the adjustment. If the top of the node is above the cell, that's not an error, so it doesn't need to automatically fix this. Perhaps it's a modeling error, where it's smoke stacking up above. All right, so this is solved. One of the first things that I do when I have solved the model is I like perhaps maybe fitting the fit the extent so I can see everything, and then I usually turn on what's called the max water depth to make sure that the model solved properly. That I do have a flooded extent. So I've turned on the max water depth. If I zoom in down here, you can see that there's a depth in the river. This is accommodated by those water level lines. If I had no water level lines, it would not show any blue shaded or rainbow color, right? Blue to red, shallow to deep flooding. As I move the cursor around here, I can see it tracks the max water depth in the status bar. Wherever I put my cursor, this is 5.09 meters deep. Over here it is 1.43. As I go near the edge, it's getting close to 0. Here's 0.29 meters deep. You can also use that section profile tool. If I just say click around here and then double click, it will actually lay that line down and show us the water elevation and show us also the DTM elevation. So again, that's showing you a map result as well as the DTM in the model. All right, of course this max water depth is perhaps interesting, especially that it shows the extent of flooding. And if I was to right click on here, I could export that. We allow the user to export the maps to a CSV file using that first command, export the current results time step. You can also export to map info, Esri grid, and Esri shape files. For example, if you picked an Esri grid file, you could pick the frequency that you wanted this information exported and choose export, and it makes the ASC file, which you could then take into GIS. Let me show you, instead of the max water depth, how about the water depth as a time series along with the velocity. And I'm going to scale these velocity vectors so that the longer the vector, the more the velocity, and the larger the head on that velocity vector. And as I step through time, and I'll make this water depth partly transparent, I'm just going to step through time. You can see the flow direction. You can see that the channel is getting deeper and deeper. And if I go to the upper left-hand corner, at this time at 11, I can just see water coming out of the manholes. Perhaps you remember that. It was very early on in the 1D simulation that this broke the ground. And so now I can see the water is flowing down the roads as predicted by it flowing on the surface. The roads were smooth, so they move at a fairly fast velocity. And you can see the flow crossing the green, my green flow line. So if I choose the flow here, I should be able to snap on this, and then I can right-click and graph it. So here is my street overflow hydrograph. You can see it peaks at around 0.37 cubic meters per second. It only lasts for about 30 minutes or less. And likewise for the head velocity points, the intersection down here, perhaps I'll just go a little bit further in time, and you can see that the water builds up before the first road in the rural spot. It starts to overflow, goes between the houses, starts flowing down the street, and let me just zoom in even a little bit more for you. Now I can look at these vectors and I can see flow going around the houses. And because I modeled the houses with a high Manning's N, that was my approach in this model, just one way to model houses. The bigger the vector, the faster the velocity, so it's going around houses. There's a preference, but you can see once it gets to this intersection, let me just re-grab that. Once it's in that intersection, it was actually flowing quite full, the street was, and with pretty high velocities. And let me grab that and graph it. So that was my water depth with the velocity. I'll kind of just go to that point in time again and zoom back in. And if I right-click on here, I can show my head velocity graphs. Here I am with my intersection. I could show the velocities as well. It's about 1 meter deep and about 2 meters per second. That's almost like a class 2 or 3 rapid going down here. I mean, get out the kayak. This would be a lot of fun. Of course, not if you live there, right? But it'd be a lot of fun to be in that water. So these maps can be exported. You have lots of control over them. You know, as I've shown, you can change the color shade, etc. You can change the length of vectors based on the property. By scaling them, I had the 30, 20, and 10 to 1. So the longer vectors are higher velocities, the smaller vectors are lower velocity. Let me go back to my PowerPoint for a moment, since I think I've basically kind of shown you the process there. And I just wanted to mention for buildings, you have this ability to model the buildings with various levels of detail. You could, for example, just draw a polygon around them to say they're inactive. In that case, water builds up around them, no water goes in them. You could trace the building with a fill area polygon and give a new elevation at which point the building becomes flooded. This is what we did in the model, where we just traced them with a land use polygon and gave a high Manning's N. In fact, our Manning's N was a value of 3. Buildings could be modeled in a very sophisticated way where you call the building a flow constriction, and you give it different layers, vertical layers, and then within the layers you can give a % of blockage. I personally like mixing the fill area with a land use polygon tracing so that the building becomes flooded at a certain elevation, and once flooded, it then has the high roughness. There's just a couple of issues that may arise when you're trying to make these connections. For example, I talked about this one where the top of the node is below the elevation of the cell. This generates an error unless you have the levels where it's automatically fixing it. The automatic fix is essentially to lower the elevation of the cell to the top of the node. Another problem which isn't automatically fixed is that maybe you're smokestacking, the elevation of the cells and the ground elevation of the node. It's not necessarily a problem to spill, but it's a problem to get back in. The land wouldn't drain well if it has to pile up a certain depth in the cell in order to get into the node. So in this case, you might want to more manually fix that, or move the node to the cell center and then regenerate the ground elevations from the tin. That would be an automated way to do it. I have just one more slide of a typical model error, and that is for the river part, the elevation in the 1D cannot go beyond the top of the node. It's a definition if you're using single links for a natural channel. You have this kind of situation. The 1D channel doesn't get any higher, it kind of puts the channel under pressure. The 2D flooding can rise higher, but this is kind of a bit of a disconnect here. So what we ask is that you raise the ground elevations of the nodes at least equal to, if not a bit higher, than the expected level of flood. This allows the channel geometry of flow to rise and be equal to the 2D flood modeling. So that's just the typical error that we see in some models. All right, looks like we've caught up on all of the questions. Thanks again, everybody. You should also know that, of course, you could send questions to us on email, and if those of you that have current expert care agreements with your licenses, of course you can contact us through our tech support group. I'm one of the people that sometimes answers questions, and I also manage that group. We've got excellent people here that are more than happy to answer your technical questions. Thanks for joining us today. I'm going to close the webinar now.